Picture an explosion so powerful it outshines entire galaxies, an event that not only marks the end of a star, but also gives birth to the fundamental building blocks of the universe. We're talking about supernovas, the cosmic forges where the elements that make up everything we know, from the iron in our blood to the gold in our jewelry, are created. Today, we'll explore how these stellar explosions transform the cosmos, crafting the essential ingredients for planets, life, and beyond. From the chaos of a supernova to its enduring legacy, this is a journey to the heart of the universe, where stars die so everything else can exist. Get ready to discover how supernovas became the alchemists of space. Let's start with the basics. A supernova is a massive stellar explosion that occurs at the end of certain stars' lives, releasing a colossal amount of energy. These explosions are so bright they can outshine an entire galaxy for a short time, radiating with the intensity of billions of suns. Not all stars end this way. Only the most massive ones, with at least 8 times the sun's mass, or specific stars in binary systems, reach this spectacular fate. When a supernova happens, it doesn't just destroy the star. It sends shockwaves and material into space, scattering newly formed elements across vast distances. This material isn't mere debris. It includes heavy elements like carbon, oxygen, iron, and even precious metals like gold and silver. Without supernovas, the universe would be a far emptier place, filled only with hydrogen and helium drifting around. These explosions enrich the cosmos, providing the raw materials for everything from rocky planets to living beings. To understand how supernovas forge elements, we first need to know how stars work. Stars spend most of their lives fusing hydrogen into helium in their cores, a process that releases the energy making them shine. This nuclear fusion is like a cosmic furnace, transforming lighter elements into heavier ones. In smaller stars like our Sun, this process stops at helium, and the star fades slowly as a white dwarf. But in massive stars destined to become supernovas, fusion doesn't end there. Once hydrogen runs out, they start fusing helium into carbon and oxygen. As the core heats and compresses, they fuse these into even heavier elements like neon, magnesium, and silicon. Each stage happens faster than the last until the core reaches iron. Here's where things take a dramatic turn. Iron is a tipping point. Fusing it doesn't release energy, it absorbs it. When a massive star's core fills with iron, it can no longer withstand the crushing gravity. In a fraction of a second, the core collapses, triggering a massive explosion, the supernova. During this event, extreme conditions, temperatures of billions of degrees and unimaginable pressures, enable the creation of even heavier elements like gold, silver, and uranium through processes like rapid neutron capture. It's in this chaos that supernovas become the true forges of the universe. Not all supernovas are the same, and each type contributes uniquely to element creation. Astronomers divide them into 2 main categories: Type 1 and Type 2. Type 2 supernovas occur in massive stars that collapse after exhausting their nuclear fuel. When the core implodes, it releases a tremendous amount of energy, blasting the star's outer layers into space. These explosions produce a wide range of elements, from carbon and oxygen to heavier ones like iron and nickel. On the other hand, Type 1 supernovas, particularly Type Ia, have a different story. These happen in binary systems, where a white dwarf accumulates material from a companion star until it hits a critical limit. At that point, the white dwarf explodes in an uncontrolled nuclear reaction, completely destroying itself. Type Ia supernovas are especially important because they produce large amounts of intermediate elements like iron, and their consistent brightness makes them useful for measuring cosmic distances. Both types enrich the universe with elements, but Type 2 tends to create the heaviest ones, while Type Ia contributes essential elements like iron and nickel. Together, these explosions ensure space is filled with the raw materials needed for new star systems. When a supernova explodes, the elements it creates don't stay still. The explosion's shockwaves hurl them into the interstellar medium, where they mix with clouds of gas and dust. These clouds, known as nebulae, are the birthplaces of new stars and planets. The heavy elements from a supernova, like carbon, oxygen, and silicon, become the building blocks of rocky worlds like Earth. Without supernovas, our planet simply wouldn't exist. But the journey doesn't end there. Over time, nebulae collapse to form new stars, and the heavy elements are incorporated into their cores and surrounding planets. In our solar system, for example, everything we see, from mountains to oceans, is made of material forged in a supernova long ago. Even we are part of this cosmic cycle. The carbon in our cells, the calcium in our bones, the iron flowing through our veins. All these elements were born in the fiery heart of a star that exploded billions of years ago. This process is ongoing. Each supernova adds more elements to the universe, enriching the interstellar medium and setting the stage for new generations of stars and planets. It's a cycle of creation and destruction that's been happening since the Big Bang, and will shape the cosmos for eons to come. Supernovas haven't just shaped the universe, they've captured human attention for millennia. One of the most famous occurred in 1054 when a star exploded in the constellation Taurus, leaving behind what we now call the Crab Nebula. Chinese astronomers and indigenous American peoples recorded this guest star, which shone so brightly it was visible during the day for weeks. The Crab Nebula is a remnant rich in heavy elements, a living testament to supernova's ability to enrich space. Another notable supernova was observed in 1572 by astronomer Tycho Brahe. It appeared in the constellation Cassiopeia and was so bright it rivaled Venus in the night sky. Tycho studied it meticulously, helping challenge the era's ideas about an unchanging universe. In 1604, Johannes Kepler documented another supernova, leaving records we still use to understand how elements spread after these explosions. In more recent times, the supernova SN 1987A, observed in 1987 in the Large Magellanic Cloud, was a milestone. It was the first supernova visible to the naked eye in nearly 400 years, and modern scientists studied it with advanced telescopes, confirming how heavy elements form and disperse. Each of these explosions has given us clues about the chemistry of the universe and how elements travel from stars to us. Supernovas don't just create elements, they transform the galaxies they occur in. When a star explodes, its shock waves sweep through the interstellar medium, compressing gas clouds and triggering the formation of new stars. This can turn quiet regions into stellar nurseries, filled with young suns shining brightly. In a way, supernovas are like cosmic gardeners, planting the seeds for the next generation of star systems. But supernovas can also be destructive. In small galaxies, a series of explosions might expel gas into intergalactic space, slowing star formation. In dense regions, like galaxy centers, multiple supernovas can fuel the activity of supermassive black holes, making galaxies shine like beacons. This balance between creation and destruction shapes the evolution of galaxies, from spirals like the Milky Way to giant ellipticals. Then there's the chemical impact. Each supernova adds heavy elements to the interstellar medium, increasing a galaxy's metallicity. Here, metal means any element heavier than helium. Young galaxies have few metals, but as supernovas accumulate over time, they become richer in complex elements, enabling the formation of rocky planets and potentially life. Our own galaxy owes its diversity to countless supernovas that happened long before the sun was born. One of the most profound aspects of supernovas is their connection to life. Without the elements they produce, there'd be no rocky planets or living organisms. Carbon needed for organic molecules, oxygen essential for water and respiration, phosphorus key to DNA, all were forged in supernovas. In a very real sense, we are stardust, created from the remnants of cosmic explosions that happened billions of years ago. But supernovas also raise questions about life elsewhere. If they're so essential for creating life's elements, could their explosions also destroy it? A supernova within 30 light-years could damage a planet's atmosphere, exposing its inhabitants to deadly radiation. Fortunately, there are no nearby candidates in our neighborhood, but the risk reminds us how delicate the cosmic balance is. On the flip side, supernovas might help seed life. By scattering elements and organic compounds across space, they could provide the ingredients for life to arise on distant worlds. Some scientists believe complex molecules found in meteorites, which come from stellar material, may have played a role in life's origins on Earth. So, supernovas don't just make life possible. They might be the messengers carrying it across the cosmos. Supernovas will keep happening as long as massive stars exist, and each one will add more elements to the cosmic tapestry. A nearby candidate that excites astronomers is Betelgeuse, the red supergiant in Orion. It could explode as a supernova in the next few millennia, creating a spectacle that would light up our sky. When it does, it'll produce new elements to further enrich the Milky Way. With advanced telescopes like the James Webb, we're observing supernovas in distant galaxies, some so old their light reaches us from the universe's early days. These observations help us piece together the history of element production, from the first stars to modern galaxies. In the future, instruments like gravitational wave detectors could pick up signals from far-off supernovas, giving us new ways to study these cosmic forges. As we explore space, supernova-born elements will be our resources. Iron for building spacecraft, oxygen for breathing on Martian colonies, silicon for solar panels, all trace back to these ancient explosions. Supernovas didn't just shape the past, they'll be the foundation of our future among the stars. Supernovas are the forges of the universe, events that turned a cosmos of hydrogen and helium into a place of diversity and possibility. From the carbon forming life to the gold we value, every element we know bears the mark of a supernova. These explosions remind us we're connected to the universe in a profound way. We are stardust, born from the flames of ancient suns. The next time you look at the sky, think of the supernovas that gave life to the cosmos and the elements still being forged, waiting for us to discover them in our quest among the stars.